Swayam Prabha. Digital India. Educated India.
Welcome to Module 9, Lecture 1. Now, Module 9 we look into special concrete. First one is of course high strength concrete, and in this lecture we will cover high strength concrete. So, what will be the outline of our discussion? Historical overview, obviously some definition, what is high strength concrete, etc., and basically the various features on strength. How do you get that high strength? Water cement ratio and high range water reducing agent, what are their roles? What is the role of aggregates, and we will discuss into properties. Paste strength as high as 276 MPa was obtained in 1930. D. A. Abraham in fact could obtain a strength as high as 276 MPa in 1930. He used a water cement ratio of 0.8, right. He used water cement ratio of 0.8. Applied pressure, high pressure, applied high pressure, and could get a strength of 276 MPa. So, you see it could even right in the beginning, right in the very early age of the history of cement based material or concrete science, one could find out that the strength could be pretty high if you have packed it properly, if you have actually applied high pressure and make it densify, and if you densify it. So, if you look at historically, if we look historical scenario, maximum strength was 40 MPa, let us say till about 1970, or let us say 45 MPa, never more than 50 MPa, no case. But currently what do we define? We define 60 MPa concrete, I am talking of cube strength, cube compressive strength, which we have discussed so far, cube compressive strength, that is up to 60 MPa. In the reference literature you will find cube strength up to 60 MPa, 28 days strength up to 60 MPa, that can be said as normal concrete. So, above 60 MPa, that is actually high strength concrete, HSC, that is actually high strength concrete. Now, IS 456 2000 and its later amendments actually has recognized M 60 to 80 MPa as high strength concrete, M 60 to M 80 as high strength concrete. So, then therefore, of course, they are talking of the grade. So, grade is 60 MPa, which means the strength is somewhere around 70 MPa, perhaps 60 plus strength to about 80 plus strength would be high strength concrete. F 28 greater than 120 MPa will be called as very high strength concrete, But many of these systems which actually tend to become cement based materials, cement based matrices, CBM I will call it cement based matrices, because they some of the ingredients of concrete may not be there. In some concrete, for example, very high strength concrete system, you may not have coarse aggregate. So, it is actually cement based matrices or cement based composite or whatever you call it. So, that is the kind of definition we have today as far as high strength concrete is concerned. But then there is something called high performance concrete. high performance concrete. Now, high performance concrete, you define now a set of performance. For example, strength is one performance, strength is one performance, strength is one performance, right, strength is one performance, strength, this is one performance. But then we have come across various kind of performances, fresh state performance, fresh state performance, hardened long term performance, hardened state performance. There are so many performances so far we have talked about. Fresh state performance like flowability, we also talked about a little bit of rheology, workability, whatever it is, ease of compaction and so on, whatever we defined, bleeding, and then shrinkage we talked about, creep we talked about, some of them could be long term, and hardening stage property, heat of hydration, generation of heat of hydration during the hydration, hardening process, heat of hydration, early strength gain, 28 days strength or hardened state strength, actually long term durability, creep, shrinkage, all these properties. There could be several performances of concrete, and many of them we have talked about so far. So, high performance concrete actually deals with a situation where a set of performance is specified, performance requirement is specified, and it must satisfy those requirements. For example, if I have a low strength self compacting concrete, this could be also termed as a high strength concrete, high performance concrete, not high strength concrete, high performance concrete. While it is not high strength, but it could be high performance. So, performance is, although most of the time high performance means strength is also a performance, but supposing I have defined certain properties at a very high level, I have specified at a given level, and that would be performances. So, high performance concrete, an analogy could be looked into like limit state design or ultimate load design. Ultimate load design used to look at only at the load, it must be safe against load, and the load is taken, that load design is taken for the ultimate load which it can carry, as opposed to working stress design, which was dealing with only the working stress situation. So, ultimate load design looks at only strength at the ultimate stage, defines one of the failure as a load failure against load, but then limit state design looks into several limits, deflection, serviceability limits, limits related to ultimate load, and so on and so forth. So, collapse and so on and so forth. So, therefore, here high performance concrete is something analogic. We are looking at many performances, and I might define a set of performance. So, strength could be one of the performance, there could be other set of performance I defined, and that should be satisfied by the concrete. So, high strength concrete is more than high performance concrete is high strength concrete could be a high performance concrete, but all high performance concrete need not be high strength, need not be, although generally it is the case, there is a link. So, that is what is high strength concrete and high performance concrete, that is what is high strength concrete and high performance concrete, their definition. All right. Then I said that water cement ratio used was 0.08 by D. Abraham, and he also found that strength is a function of water cement ratio. In this manner it reduces. So, therefore, if I have low water cement ratio, strength will increase, and if you can pack it so well, you can get very high strength. So, therefore, this was understanding during D. A. Abraham's work, from D. A. Abraham's work, right. This was the understanding from Abraham's work, but then T.C. Power and their team actually found out the porosity, and they could link water cement ratio to porosity, capillary porosity, and this we have discussed, and we have actually talked in the very first module itself. So, porosity and lower the porosity, better is a durability as well as strength is higher of hardened concrete. This is what we have seen through our discussion. So, therefore, the whole idea to get higher strength I must reduce porosity, but then I also talked about, if you recall, pore size. For the same porosity, smaller pore sizes will give you higher strength. So, reduction of the porosity and refinement of the pore sizes are important for high strength system. So, if you want to get a high strength system, then you must reduce down the porosity and you must also refine the pore sizes. Now, all this idea that came through over the years that result in high performance concrete, densified with small particle system, we will look at that, macro defect free matrices, reactive powder concrete. So, these are results of this kind of early breakthrough which gave into later understanding or later improvement, by reducing down essentially pore sizes and porosity. That is what it is. So, we will look into all these high strength matrices later on. Now, we will concentrate into high strength concrete, etc. Now, we said that if you want to get high strength concrete, then you must refine the pore and you must reduce the porosity. This is the main crux of the matter. And therefore, how do you do it? Well, you use a fine pozzolanic material such as silica fume, which we have discussed earlier, and you got to use low water cement ratio. That is what the idea we said, that water cement ratio must be lower, and this lower water cement ratio means you should be able to use some sort of water reducing agent, and obviously the aggregate size and other things packing must be appropriate. So, basically aggregate size and packing, that should be appropriate, packing should be appropriate, this is packing. All right. Now, just let me go a little bit historical. We have looked into all the pozzolanic material in the very cementitious material in the very first module, one of the earlier module we have looked into these materials and also looked into their history, little bit of their history also we looked into. Now, remember, this is a little bit linked to other industry as well, because this is a byproduct coming out from silicon industry or ferrosilicon industry. That is what we have looked into in the beginning. Pozzolanas were used for very long time. Historically, pozzolana were used 2000 or even more, that kind of time, historic times, just after prehistorics maybe time. From that time, Roman Empire used the pozzolanic material. So, there are the volcanic ashes. Then came, I told you, the lime and silica combinations were used, various ways, various part of the world, including India, where we use surki and so on and so forth. Now, this gave rise to cement, but then material like fly ash became essentially from the environmental concern and reduction of the cement, which was costlier, which is a costly material in the cement based system. To reduce that, as well as from the environmental concern, fly ash has been used, but fly ash is not as fine as this. So, this was because thermal power plants came. So, like 50s, 60s thermal power plants came. So, 70s you used research on pozzolanic material, like use of fly ash was there. Blast furnace slags were now available, therefore, slag cements were also there. So, those research continued, but the electronics industry, semiconductor industry started developing in 70s practically, although solid state electronics might have started from 1950s. I mean the research of transistor and all that, they started from 40s, late 40s and 50s, but the silicon as a material, its importance started possibly in 70s and 80s more. So, silicon industry or ferrosilicon industry grew, and that gave us the product like condensed microsilica or silica fume. So, it is only 80s when this material became available, and if you recall that this material is highly pozzolanic with a very fine size, rich in silica, that is what we discussed earlier. So, this material is finer than cement, and therefore, the fine pozzolanic material that became available as a byproduct from some other industry, which was which actually people started looking into its utility, and that is how the high strength concrete could come in 1980s and 90s and later on, of course. So, therefore, there is a historic reason why did it come, the other material was not, even before that material was not perhaps known, but not to the great extent that was there, and it was available, it was definitely limited. Today also it is not available everywhere. For example, in India we have to import it and it is costly. However, this is the material, together with this material made it possible for high strength, made it possible to produce high strength concrete, all right, because this material is finer than cement. There are other routes tried to improve the strength of concrete, namely polymer concrete, which we will discuss sometime later on. Polymer cement concrete with rubber latexes, again we will discuss sometime later on. But they were costly, they are still costly route actually, but this gave us a viable way. After the ferrosilicon industry's development took place, this gave us a material which could be used, and this fine pozzolanic material, silica fume. Now, water cement ratio reduction, so that's one thing. Second issue is water cement ratio reduction. Now, if you want to reduce water to cement or even water to cementitious, there is a minimal required for standard consistency. We talked of it earlier, that at least you require water for standard consistency for the paste, otherwise paste itself will be somewhere dry, somewhere solid. So, it will not be simply workable, proper dispersion of the particle would not be there. So, you could not have gone to a very low water cement ratio, but for the construction chemical development. Now, historically when you looked at the admixture, you could remember historically lignosulfonates came pretty early, 1930s even. This we mentioned sometime earlier, 1932, but the melamine and naphthalene formaldehyde condensates, sulfonated melamine and naphthalene formaldehyde condensates, they came in 1970s, synthetic ones, and then polycarboxylate ether came later on, 80s and so on and so forth, with the what you call hyperplasticizers or very high range, ultra high range water reducing agent and so on and so forth. So, now this could actually disperse the cement or cementitious particles significantly, and thereby increase, or the water required for consistency could be reduced. So, low water cement ratio could be achieved only when you have high range water reducing agent. Otherwise, you will have to apply a high pressure to get that kind of strength, like in the paste. Concrete, of course, it would be fairly difficult, technologically may not be a viable situation. So, therefore, this to achieve this played a big role. Now, this is anyway required, but these two things are the high range water reducing agent and the mineral admixtures. Now, that brings us to the situation that actually 6 component rather than 4 components concrete, 6 components rather than 4 in concrete, 6 component concrete rather than 4, 6 component rather than 4 in concrete. So, basically earlier we are using cement, water, coarse aggregate, fine aggregate, 4 components, 4 components. That is very conventional, very old. Even modern engineered concrete of any strength should preferably be 6 component, because the 5th and the 6th component will allow it to reduce cement and get better property, make it cheaper, economical, more sustainable. So, modern concrete all should be 6 component, but high strength concrete cannot be 4 component at all. High strength concrete cannot be 4 component at all, it has to be a 6 component rather than 4 component in concrete, 4 component concrete. So, the 6th component is, 5th is this and 6th is this. 5th is this component, 6th is this. I mean, could be any other material of the possibility, should be possibly any other material, but should be fine and should have also some kind of reactive scenario, which can improve the porosity, reduce the porosity and effect in pore refinement. Silica fume is able to do it, some other material may come, some other in future, and which might be able to give it, but at the moment it is silica fume which is very which is for example, people are trying processed ground granulated blast furnace slag, or maybe processed metakaolin or some other material, which should, but then whole idea is that it must act, should be able to go into the interstices of the cement system itself, and also affecting some kind of additional bond formation in future, not only just the filler effect. Because if it goes into the interstices of the cement system itself, it will act like a filler, but if it has some kind of bond, the filler would act much better. Now, high range water reducing agent in addition to CW, FA and CA. So, these two more components. So, it is a 6 component concrete has to be. As I said, it is not only high strength concrete, but any concrete, modern engineered concrete should be 6 component, why not even n component, some more admixtures which will come in future, and they will improve the properties in much better manner. So, a generalized system could be n component concrete, with this 6 is definitely maybe 7th, 8th to improve properties in some other manner, some other properties and so on and so forth. So, you see this, if you look at it, the old concrete, air entrained concrete was this one. You had, this was the volume of air, water, and air entrained concrete was very common in the West. In India, you may not have done air entrainment, but this will be still less, voids should be less actually. This was a cement which was relatively less, but then large quantity of water. This is your fine aggregate and this coarse aggregate. And if you look at the high strength concrete, this has got significantly reduced from here, it has got significantly reduced here, and you have cement plus supplementary cementitious material. These are the relative volume, air volume we are reducing, the void volume in the just hardened state you can think of, water volume which is actually reduced in the system, and cement, and this is mineral admixtures, and then fine aggregate is this, and coarse aggregate is coarse aggregate is this is your coarse aggregate. So, fine aggregate, coarse aggregate. So, what you see, actually this is now, instead of this you have got the mineral admixtures here, the water has reduced, water has reduced, water has reduced, water has reduced, this has reduced, this has become more, this has reduced, this fines will also increase, but this has also reduced, because this will be now, although they might occupy similar volume, but to accommodate this more volume of the paste, more volume of the this paste, you need possibly more sand in the system, reduce down the larger aggregate, that would have implications on interfacial transition zone as well as some shrinkage. We will discuss this sometime later on. So, 6 component concrete rather than 4, 6 component. Now, because to reduce this you need a high range water reducing agent to make it compaction possible, workability possible, workable concrete pumping possible, and so on and so forth. You need to have, to reduce this, actually you need the 6 components. So, you can see that 1, 2, 3, 4, 5 plus the 6 component is a water reducing agent. This is a must, and as I said, there could be even more. So, that is what made it quite possible, the high strength concrete. That is the that's what made it possible, high strength concrete. So, this is what the reactions we have looked into. So, typical C3S reaction would produce CH, and this CH together with the silica fume will produce CHS gel. So, this is a secondary pozzolanic reaction. This will be the case in high strength concrete too, and this is essential. Of course, in normal concrete you will have also, if you add pozzolanic material there. So, reduction in outer products with low water cement ratio. Remember, we talked of inner product and outer product. This is the original cement grain boundary, the hydration product inside this, we call it inner product, and outside this will be outer product, but if you have low water cement ratio, outer product required will be low, and filler effect with this fine mineral. That means, fine mineral will go inside the particle itself, fine mineral will go inside the cement particle itself. These are your cement particle. Let us say I have got fine minerals which will go inside this, which will go inside this, and they will also be pozzolanic. So, they will react, and you remember we talked about the hydration process of all different kind of mineral admixtures and so on, right in the first module itself. That is what would make possible the high strength concrete. High range water reducing agent for deflocculating, and this will improve the ITZ porosity and lower the ITZ thickness also. I will come to this a little bit later more, how it actually reduces the ITZ thickness. I will just come to this in a while, right. So, okay, presence of aggregate size, I will come to the ITZ reduction a little bit later. Now, aggregate particle introduces stress concentration, that is what we know at the interface, and volume region of stress around aggregate increases with aggregate size. So, basically you know the interface is very important, that is what the weakest link, and we have seen most of the time the crack starts from there, So, therefore, it is important to improve the interfacial transition zone. So, aggregate particle larger the size, actually it increases, the more stress concentration will be there, because surface area is less, large size means surface area is less. So, the same stress if it has to pass, there will be more stress concentration, and volume region of stress around the aggregate will increase, right, volume region of stress concentration. So, this the weakest areas, weakest volume will increase. For higher strength concrete is stress concentration. So, this we have seen earlier when we were talking of strength. For higher strength concrete, stress concentration around the aggregate, discontinuity is there, and lowering of bond area dominates, therefore, we use lower MSA, because bond area will be reduced, same volume of aggregate, let us say, one with a larger size aggregate, MSA being higher, that means your finer proportion will reduce, total surface area of the aggregate will total surface area of the aggregate will increase, total surface area of the aggregate will increase if you have finer material. So, if you have coarser material, so MSA is higher, you will have less surface area, less surface area. So, the bond area actually, the stress concentration will be higher in such situation. So, all these discontinuities at the interface, stress concentration, bond area, all this actually dominates. Thus, we use generally lower MSA, and this we have looked earlier also, and we are just reiterating what we said earlier, that MSA should be lower in case of high strength matrices. So, generally you have much lower MSA in this sort of matrix. With low porosity paste, its content is increased, thus aggregate content is reduced, and lower is the dominance of ITZ. So, fine aggregate again you might increase, but volume, even if the volume of the material remaining same, volume of the paste, etc., volume of the paste will generally increase. So, there is generally aggregate concentration or volume of the aggregate also reduces somewhat, volume of the aggregate would be less also. Sometimes this reduction in volume is required in very high strength system, in order to ensure that there is bulk shrinkage. For example, shrinkage in the bulk, whole material shrinks, rather than shrinkage like this, this is your matrix, and you have got lot of aggregate, let us say lot of aggregate. So, the shrink, because this portion shrinks, this portion shrinks, this portion aggregate portion shrinks, the paste portion shrinks, aggregate do not shrink. So, you might have cracking here actually, crack could be developing here, because of this shrinkage of this one, shrinkage of this one, shrinkage of this one, but shrinkage of this one, but no shrinkage of this one. So, essentially bulk shrinkage can reduce, it can actually introduce a kind of compression here onto the aggregate and improve the interfacial bond. So, this can reducing the aggregate quantity in higher strength system might have an advantage in terms of this as well, right. One thing is reduction on the interfacial transition zone volume itself, other would be even shrinkage, bulk shrinkage, the whole thing will shrink together. So, if there is an aggregate, this will also, since everything shrinks less aggregate. So, therefore, this would actually might compress the aggregate itself. So, this is one fact which should be useful to understand very high strength concrete, why it does not use very large size aggregate. Cement, it should be good quality OPC, preferably higher quantity of C3S and C2S with low C3A, higher quantity of C2, C3S and C2S with low C3A. because this will ensure higher CH formation and less heat of hydration, because this is the one which is is responsible for heat of hydration. It has got the highest heat of hydration. So, heat of hydration will be reduced if I have less C3A, and this would generate a lot of calcium hydroxide, which can actually react with the pozzolanic material to improve the properties altogether. So, more CHS. So, this will also reduce down secondary effect of conversion. Now, what is conversion? If you remember, we talked of high alumina cement or hydration process of cement system. We said that initially first it forms ettringite, which get converted into monosulfate, and volume of ettringite, if it is higher than the monosulfate or the final product or the sulfate that forms in the later situations from the ettringite, then if their volumes are less, it would actually introduce new pores, because originally it was larger volume, after and later on if it occupies lesser volume, these voids, this would generate a kind of voids. Now, they become important in very high strength system, may not be as important in low strength system, because there are already existing lot of pores of other kind, but here you are trying to reduce all other kind of pores. These pores may may become dominant. So, therefore, secondary effect of conversion and low heat of hydration would actually, it would be better if you have low C3A content. Low water cement ratio. So, C obviously is usually greater than 400 kg per meter cube. Cement could be finer, which will be easily reactive, but should not be too fine to improve or increase the high rate of hydration. So, some people use 53 grade of cement, 53 grade of cement by Indian standard, but it is not necessary that you use a high strength or finer cement or higher grade of cement, higher strength cement for producing high strength concrete. Even 43 grade can give you good results. High heat of hydration will surely be lower in such situation. So, cement should be of good quality of this kind for high strength concrete. Low water cement ratio. Water cement ratio should be less than 0.3, and therefore, would need water reducing agent for consistency, that we have seen. We have already said that this is what we need for high strength concrete. So, what we are seeing, good quality cement, preferably with low C3A content, then water cement ratio should be lower, and you would need obviously WRA. With low WC, lower C, fine pozzolana is used. So, use fine pozzolana together with this, and its effect is something like this. Water cement ratio ranges from 0.20 to 0.22 to 0.3. Usually lower than 0.2, there are other kind of problems comes in. You may not get simply, you may not get high strength concrete system. In fact, strength might even start reducing, unless you do something more, maybe heat treatment, pressure, and those kind of things. So, lower water cement ratios, lower may require heat and pressure treatment in case of very high strength matrices. So, basically otherwise you may not get that improvement. So, generally high strength concrete we restrict to usually 0.27, 0.28 and so on, so forth. Water cement ratio is this, but very high strength system you might get still lower, but below 0.2 might require heat pressure treatment for improvement in the strength, higher strength. So, let us see how does water reducing agent works. This is where cement, before they would be touching each other, before you have added any without any high range water reducing agent, kind of flocculate together, but you add high range water reducing agent, they get absorbed onto the grains, and they would result this kind of dispersion. And this is what we have seen already. We have discussed this. I am just reiterating the whole thing. So, this was the scenario with high range water reducing agent, they get better dispersed, they get separated out, and when you are adding water reducing agent together with the silica fume, no superplasticizer, this is the situation. With superplasticizer, this will be the situation, and when you have silica fume or such fine material, they will just penetrate, and fill in into this interstitial space. So, this one get pushed apart and they are dispersed with high range water reducing agent, that is sulfonated melamine condensates or sulfonated naphthalene condensates or polycarboxylic ether type of things. This is of course the most is most effective, and this with the silica fume, you will find silica fume going into the interstices. So, when you add this, they push them apart just as a touch, and they were not agglomerate kind of forming a kind of clog on large bonds inside this. So, they are now more or less reduced, and when silica fume you put in, they go into the interstices of the system, and thereby the voids actually would further reduce. So, what is happening? You have fine material going into this interstices, fine material going into this interstices. So, the pore sizes which were quite large here, they are very large here, they are very large here, very large pore sizes, where outer product will anyway deposit, but still leave some void if the water cement ratio is high. When you have dispersing agent, they will obviously get reduced with a lower water cement ratio, surely they would, and this is the thing. But if you put fine pozzolana, the porosity will further reduce because of those fine material going as filler, but they has to be dispersed and they should go well within the pore space, and therefore, this together with this helps, and you will have pore sizes reduction also. So, in the bulk paste you will have reduced porosity as well as pore size reduction because of two effects. One is a filler effect, other is a secondary pozzolanic reaction effect. So, they will fill in, they will get in and they will fill in those spaces. As the hydration occurs, they will further improve this situation. So, that is why you need this system to get high strength concrete. If you look at, if you recall, we talked about this. This is without silica fume and this is with silica fume. So, porosity, total porosity, this axis is cumulative intruded volume of mercury. So, if you do a mercury porosimetry, how much mercury has altogether penetrated? Originally it penetrated more per kg, or whatever it is in some volume or volume per unit volume or per unit mass, and this is originally it penetrated, that means porosity is more. Now, after silica fume this is reduced. Not only that, you see the maximum size here is this, where maximum size here is this one. So, therefore, there is a reduction in the size as well as volume of the pores. Both sizes of the pore would reduce and volume of the pore will also reduce. Now, that is what we have seen, because it goes into the interstices of the cement system and therefore, reduce the porosity, act as a filler. And further, now it will be the interstitial pores between the silica fume themselves. It will be the simply the pore sizes will be governed by these spaces, the interstices space within this system. Interstices, if I look at this interstices within this area, within this post area, where the interstices of the particles they will govern the pore sizes, and that is why they are able to reduce down the pore size so much, because pore sizes within the silica fume particle, and so this is not between the cementitious cement particle. So, therefore, this is able to reduce down the pore sizes as well. So, that is why silica fume together with high range water reducing agent are able to reduce the porosity as well as pore size distribution, and therefore, improve the strength of the paste. If I may call it cement silica fume paste, its strength will be improved, significantly, right. This has been observed by some people, and they find the paste strength with silica fume content, of course, it does not change much. Content wise it does not change much, there is a reduction, the strength of course is 5%, 10%, beyond 15%, then it is not able to go into the interstices anymore, but you are adding only silica fume alone. So, pore sizes will be smaller, but the total porosity might even may not improve any further. So, this is one experimental results. Supposing I add 20-30% silica fume, they will be packing, they would be actually too much quantity. So, they will not only they will push the cement particle out, and the porosity within or the pores within the silica fume system will start dominating. That is what we talked about when we were talking of particle packing, when we were talking of packing densities and so on. There is an optimal proportion at which actually your packing density is maximum. So, here also silica fume is acting as a filler. So, since it goes as a filler, there is an optimal quantity. Besides that, actually they will also reduce down the porosity by their secondary reaction. So, adding large quantity of silica fume does not help, not more than 10-15%, rarely more than that. I mean, it will never be more than 15%. Third aspect, of course, is the cost of it. It is not a very cheap material. So, it might be costlier than cement, as I said, where if you are importing. In India, it is about 7-8 times costlier than cement. So, therefore, you you can only use it in limited quantity, but it is used that in an engineered way, so that its advantages is realized in full. So, the strength of the concrete, paste strength increases in this manner, but the concrete strength increases significantly. Now, we will come to that. Why does concrete strength increases significantly? Because concrete strength is governed by interfacial transition zone. An interfacial transition zone improves. Let us see how does it do. Let us just see. Okay. So, ITZ will be improved. So, it has been observed that 0% silica fume and 15% silica fume, this is your 15% silica fume situation, 0% silica fume, right. So, this is the distance from the bulk paste aggregate surface concrete and volume of pores with silica fume. Of course, bulk paste close to the aggregate 0% has got high porosity. This is no silica fume, no silica fume, no silica fume, no silica fume, no SF. So, you have got close to the interface, it is in micron. So, around 5 micron, 10 micron, you have got no SF, high porosity. But if you put silica fume, this gets reduced, and bulk paste, of course, they will be more or less similar. Bulk paste, no this. So, this is with SF, with SF. So, bulk paste, their porosities are similar, no SF, but particularly this one it improves, and that is why concrete strength improves significantly. Now, how is this possible? So, this was earlier our, say this is aggregate, and this was my cement particle earlier, aggregate prior to silica fume addition or without silica fume. So, this is my interfacial transition zone, which will have porosity of this kind, which will have porosity of this kind, this will have porosity of this kind, interfacial transition zone, pore sizes and porosity, and transition zone thickness would be largely governed by, you can say half, this is the thickness would be half average size of cement particle, we can assume that, or slightly more, maybe somewhat more. Now, what I do, I put in actually silica fume there, I put in silica fume. So, these are my silica fume, they will come and pack in here, they will come and pack in here. So, what will happen if they are sufficient? Now, the ITZ will be governed by, ITZ thickness will be governed by dimension of the silica fume, half average size of SF, because it is that SF which will pack here, it is the SF silica fume which will pack here, silica fume which will pack here. It will be the at the interfacial transition zone, it is a silica fume which will pack in this manner. Still there will be some interfacial porosity, transition zone porosity, but silica fume which will come and pack in there would reduce significantly the ITZ porosity and size of the ITZ porosity, improve, and secondary pozzolanic reaction actually will fill in also this space. So, therefore, that is why we saw that there was significant increase in the concrete strength, because ITZ porosity improves significantly with addition of silica fume and water reducing agent, and this could make it possible. So, I am talking of silica fume, it is not necessarily the material with silica fume, it could be any material which is fine and has got similar properties in terms of particle size and pozzolanic properties. So, any material having similar kind of properties, not necessarily silica fume, any material, and also similar kind of packing characteristics. It is important to understand the silica fume particles are also spherical in nature, which you have seen earlier. So, it should be able to pack and reduce down that ITZ porosity, and if it is spherical, then dispersion is also easier. right. If it is not so spherical, dispersion may not be easier, packing may not be easier. So, any pozzolanic material or very fine pozzolanic material which can go and improve the ITZ porosity would actually be useful in making high strength concrete. With fly ash also, if it is a fine fly ash, you might be able to make the same high strength concrete, because if it is solo, as long as it is able to improve the ITZ by, and it is fine and it is able to get into the interstices of the cement system, then it will be fine. But all fly ash particle, because their silica content is relatively less. So, the pozzolanicity also is relatively less compared to silica film. So, anyway, these materials we have looked into right in the beginning in the first module, and we understand their behavior. Therefore, if we get something derived out of them judiciously, we can use and make at least some strength, maybe 60-70 MPa concrete would be much easy to produce, even with some good quality or processed fly ash and so on and so forth, or processed GGBFS or processed metakaolin, right, depending upon their fineness and pozzolanicity, etc. So, that is what I was saying, that we discuss about the interfacial transition zone a little bit later, and that is what we talked about. So, that is how they are able to improve. Now, what about the aggregates? Well, I should have a continuous grading and good packing characteristics. Continuous grading means right from cement or silica fume size to the MSA. There should be a continuous grading. Now, this situation can well be understood. I will come back to this. Let us see this diagram and we will go back again. This is the one I am talking of. You see, it is a continuous grading is the best thing to have. Continuous grading is to have a best thing. So, I might mix up everything, fine, that is your these are sieve sizes in millimeter, fine material, somewhere the fine material and the coarse material, but I should have grading starting from absolutely fine material of 0.001 millimeter, which means the micron sizes. So, this is the final grading. So, this is the micron size particle, this is actually we are talking in millimeter, this is in millimeter. So, if it is in millimeter, 0.001 millimeter is actually micron, 1 micron, submicron sizes. So, the submicron size, micron size, sand size, coarser size basically 0.1 to 1 millimeter to about 1 millimeter, right. So, 1.18, these are sand sizes or coarse fine aggregate sizes. This is also fine aggregate, this is about coarse aggregate. So, 10 mm size. So, this is coarse aggregate, again coarse aggregate. So, I might have all combinations and make a grading such that my packing density is best with everything put together, it is the best. So, when I am looking at aggregate, I can't look it in isolation from the paste system. Therefore, I look into the packing of everything. So, everything should give me the best packing, and best packing would also involve volume of paste and rest of the material, the coarse aggregate solid material that is there in the concrete system. So, good aggregate packing is very, very important in case of aggregate packing, continuous grading and aggregate packing. But I would say that today continuous grading is not an issue, because we must look at the packing densities, and which we have talked about. So, you can find out the packing density of your aggregate system and determine the quantity of paste there. We have also talked about a mixed design procedure using this kind of concept. So, therefore, one can actually find out the packing density of your different aggregate combination, find out the optimal packing density, and then use the paste slightly more than that, and it could be still more than that if it is a very high strength system. Why? To reduce down that shrinkage, allow bulk shrinkage, reduce down the shrinkage. We will look at that sometime later on. So, lower MSA obviously to avoid stress, concentration and discontinuity you have talked about. So, MSA will be lower, good packing characteristics, best packing density I will say, and then it must have high modulus and high strength, because if it is strength is lower, this can restrict the strength of the concrete system itself. So, therefore, because it is against weakest link. So, use a poor aggregate, paste strength you improve, it is not going to help. So, therefore, your aggregate must have high modulus and high strength. And MSA, that is why never rarely exceed 10 mm, 12 mm, although people could get some 60, 70 MPa with 20 mm, but 20 mm aggregate, but it is better to use lower, if you are not finding the strength, reduce down the MSA. So, generally high strength concrete system 10 mm, MSA very high strength system, very high strength system, there will be no coarse aggregate. We will come to that sometime later on when we talk of reactive powder concrete. You see, basically in normal strength concrete, if I look at stress strain diagram, stress in MPa, strain here, cement paste is like this. Aggregate, both are brittle anyway, aggregate will be somewhere up there. So, the basic overall stress strain diagram of the concrete will be somewhere in between, all right. So, aggregates are natural system, they have their own strength, and that is usually higher, we rarely realize this. It's like we rarely realize this actually, we have, because it is controlled by this, but in high strength concrete I improve this cement paste, therefore, this value goes up here somewhere there, if I take it, if I make it here, and this would be somewhere there, or if I bring it down, this strength increases because of this would go up, this would go up, this whole curve goes up because this pushes it up. So, we improve the cement paste, we improve the ITZ, and therefore, my aggregate and my cement concrete improves. Now, remember, if I have this one somewhere there, then the strength would be reduced. So, I must have a good high aggregate strength, and modulus of elasticity also should be higher, because you remember critical stress is a function of modulus of elasticity of the concrete system without pores. Now, the modulus of elasticity of the concrete system is a function of the modulus of elasticity of aggregate and as well as the cement paste. So, therefore, critical stress will be lowered if I have lower modulus of elasticity, so of aggregate. So, therefore, one must look into this, it must have good modulus of elasticity, good strength. It is like balanced design. If you must have done RC design, where we try to do a balanced design, where strength of the concrete or concrete and the steel fails together. So, this is a balanced system. Now, here actually ITZ was failing earlier. I have 3 component, I will say the matrix, I have the paste matrix, the ITZ and aggregate. So, if all of them fail together, that would be a most efficient system. So, aggregate, ITZ, paste, everything should fail together. So, earlier when paste strength was low, ITZ strength was poorer, they would have dictated the strength, but as soon as I increase the strength of this 2, paste and ITZ strength I increase, the aggregate everything may fail together. So, what you see is in case of high strength concrete, if you are crushing a cube, you might see the crack passing through the aggregate as well. So, it is not only the interfacial transition zone and bypassing the crack, the aggregate themselves, going through its boundaries to the bulk paste and joining up again the aggregate interface. This may not be the case here, you might find that it passes through the aggregate itself, because it is almost a balanced system where efficiency of everything is being utilized. And how do we do it? By improving the ITZ through fine material, pozzolanic material which can get inside, and water reducing agent which will disperse the particle and allow finer material to get into them, get into the interstices of those cementitious particle, and both at the interface of the aggregate system at ITZ as well, and improve this porosity and refine the pores. So, that is the principle of high strength concrete. That is the principle of high strength concrete. Just aggregate properties, if you look at it, for example, modulus of elasticity, compressive strength and porosity of some of the aggregate, let us say quartzite rock, some 87 MPa would be the compressive strength, 42 is the modulus of elasticity, porosity is 1%. Mortar, if I prepared with this quartzite fine particle, I get modulus of elasticity is slightly reduced. If I produce concrete, then I can go to 99 MPa, because if I improve my paste, it can show you good strength. See, this is better than mortar is here and the concrete is somewhere there, because I will add quartz aggregate then, and this might brings down the strength somewhat. Larger, finer the particle size, strength will be higher. We talked about that also, because all the fractures have already occurred, right. In a large size aggregate, this we talked sometime earlier. Larger size aggregate, there are some failure planes already existing in the aggregate. So, when I crush it, this crushing the separation has already occurred in the fracture plane. So, therefore, more surface energy it has already absorbed, and it has it is actually fracture energy it has dissipated, and therefore, it is more stable. Finest material is more stable and its strength will be much higher. All right. So, therefore, size quartz aggregate, when you introduce, strength could be reduced somewhat. You see rock limestone 115, 106, this is also concrete is 106, and this is sandstone 147, concrete is 107. In between mortar is not available. Modulus of elasticity is 40, here 39, 49 and 45 and so on and so forth. So, concrete the rock has got 49 modulus of elasticity. So, both properties the porosity is given, this is highly porous material. So, therefore, rock strength although is high, this can bring down my strength, because the cracks will pass through this, and therefore, concrete strength gets reduced. 147 although its strength is, it cannot exhibit that kind of strength. This we have already discussed, the particle packing. So, therefore, quartzite concrete is somewhere here, stress strain curve, sandstone concrete somewhere here, limestone concrete, stress strain curve is somewhere there. High strength concrete therefore, would exhibit a higher strength, but it will fail at lower strain. This is not a problem, but we must know it, because brittleness, the ductility of the concrete, we know that concrete is weak in, it is brittle. Therefore, we reinforce it to get the ductility, or we add fibers to get pseudo ductility in micro level. So, that kind of thing. So, therefore, this is not a problem, this is no advantage neither, this is not a, but negative aspect also. So, because high strength matrices, we do not rely on the ductility of concrete, we really rely on the ductility of the reinforcing material. So, therefore, this in ordinary reinforced concrete structure is not a problem, but there are other places where we put in fiber to improve, for example, engineered cement composites, microfibers might be added to improve the strength. So, but we know that its strength is higher, modulus of elasticity is higher. If I look at its other properties, this is tensile strength, this is compressive strength 1 for normal concrete, ordinary concrete. So, relative strength I am talking of, tensile strength may be 3 times more, while its compressive strength may be 2-5 times more. So, relative strength of high strength concrete, if it is 2-5 times more compressive strength, then tensile strength could be of the similar order or slightly higher. Then this is modulus of elasticity, definitely higher. These are the fracture properties, the various kind of fracture properties. I will just define them. Some of the fracture, some of the fracture properties, for example, energy absorbed will be lower. The length of the fracture length around the tip would be lower. So, some of those things are lower, which is actually sign of brittleness and so on and so forth. So, some properties, strength obviously improves, tensile strength also improves, modulus of elasticity also improves, not to the proportion of the compressive strength, but it improves. So, one got to, there are people who have done some research on those from the design point of view. We are talking in terms of just general ideas. Modulus of elasticity will surely improve, but not as much as the compressive strength. Tensile strength improves further, but other fracture properties also improves. So, high E, low fracture toughness, because energy absorbed is less. Stress strain curve, area under the stress strain curve is lower now. It was somewhere here, now this area is lower compared to this. So, therefore, toughness could be lower. Very good durability, because low porosity, nothing can enter, but one must see against magnesium sulphate, because magnesium sulphate can attack the CHS itself. So, the it's still good against all sulphate, all kind of durability, because its strength, it does not allow anything to penetrate through it. Improved mechanical properties. So, fracture energy, KIC stress intensity factor, this is lower, fracture energy is lower, L0 is the dimensions of microcrack zone ahead of the tip advancing crack, these are lower. This is lower, this is lower, that is what we have seen. That is what we have seen earlier. This is lower, this is significantly lower. So, this is around the crack, the micro cracking zone, and fracture energy is of similar order, and this KIC is the intensity factor, fracture intensity. So, this stress intensity factor are similar. So, these are some fracture properties, this is like this. Fire property is suspect, some people say it is not very good against fire, unlike the conventional concrete, because of its low porosity. When hydrated water wants to get out of the system, it has no way to get out. One of the theories put forward, therefore, there are cracks. CHS gel, when it breaks down under fire, if you heat it to 600 degrees centigrade, 500 degrees centigrade to 600 degrees centigrade, CHS gel will break down. So is calcium hydroxide. So, when they break it down 700, 750 degrees centigrade, calcination of like calcium hydroxide will break down, and it will go out, it will remain as calcium oxide, and water will H2O will grow. Now, water does not have a way to get out, because it is fully dense, no porosity. So, therefore, cracking may occur, spalling occurs easily. So, fire property is suspect. One has to see what properties are good and what properties are not good, but we have seen that its strength is very good, durability is also very good, and we have also seen the fracture properties. Creep, shrinkage, etc., has also to be seen in this light. Their properties also to be seen. So, maybe next lecture we will look into some of this. So, today in this lecture we have looked into high strength concrete principles, and we have looked into some properties. Next class we will look into the additional properties, whatever is left, the mixed design procedure, then we will look into other high strength systems. Thank you very much.